Do you think it would be sensible to just sit here admiring the scenery while they cut down this tree?
Well, I don't know if it would be sensible. It would be a bit wiser, though, if you could actually calculate the height of the tree. And you can actually do that if you know a bit about angles. Now, let me illustrate with this carpenter's rule that I always carry about with me, as you can guess. Intuitively, we'd imagine that this is an angle. It's a small angle. This is a bigger angle. What about this? In fact, this is the same angle as I had previously. What about this? Same angle again. You see, it doesn't depend on the legs. What we need is some way of measuring angle in order to be able to do calculations using them. And we're going to measure angle by using movement in a circle. If it's a circle of radius r, then the circumference is given by 2 pi r. Well, actually, it's clear that if you want to measure angles, all you need is a horse on a lunge rein. But actually, it's clear that the horse is tracing out an increasing angle. And what we'd like to do is to start off by measuring one of these angles. So let's measure the angle that the horse has stopped at. That's the angle that the rein has made. And now I knew this meter stick would come in useful, so let me pace out meters. And I've got 1, 2, 3, 4. So in fact, the horse has traced out an angle which is measured on the circumference by 4 meters. Well, let's try measuring that angle again. I suppose the horse is getting a bit dizzy, so let's increase the radius. Well, what about the angle now? In fact, I can see it's exactly the same angle as before. So let me measure it by pacing around the circumference. Well, I'll use my meter stick and take meter paces, and I have 1, 2, 3, 4, 5, 6, 7, 8. Well, that's very funny. I have exactly the same angle, but now I need 8 meters to go around the circumference, and last time I had 4. But that must be because we've changed the radius. Let's see, what happened before? Well, in fact, the present radius is measured by 1, 2, 3, 4, 5, 6. It's 6 meters, and the old one I can see is 1, 2, 3. 3 meters. So in fact, all our measurements have changed, and yet the angle has remained exactly the same. Well, remember, when we doubled the radius, we actually doubled the arc length traveled. So the ratio of arc length walked by the horse over radius remains the same. So that must be the basis for our definition of the measure of an angle. So let me write that down. So when the horse traced out that angle, the first time it walked 4 meters, the second time it walked 8 meters, but remember, the first time the radius was 3 meters, and the second time the radius of the lunge rein was 6 meters. And it's that ratio which is the same each time. So it must be that number, 1.33, which gives us a measure of the angle traced out by the horse. Let me go over that again. This angle has an arc 4 meters long for a circle of radius 3 meters. So for this angle, the ratio of the arc length over the length of the radius is 4 over 3, which is just 1.33 in decimals. Now, we can make the radius longer and enlarge the circle, but keep the angle the same, even though both arms are longer. What happens to the ratio? Well, the arc length is now 8 meters, and the radius measures 6 meters. Our ratio? 8 divided by 6 is still 1.33. And for the same angle, we get the same number, whatever the size of the circle. Each angle has its own particular ratio, which stays constant whatever size circle you look at. The number we get as the ratio is a measure of the angle in radians. Well, what about some other angles? For example, this angle is 0.5 radians. The ratio of arc to radius is a half. Here the angle is just 1 radian. The arc is the same length as the radius. This angle is 2 radians. At this point, the angle is 3 radians, and so on. For a right angle, we can calculate the number of radians. With radius r, the whole circumference is given by 2 pi r. And a quarter of that is the arc of the right angle. Well, that's just a half pi r. So the ratio of arc over radius, a half pi r over r, is just a half pi. So in radians, a right angle is just pi over 2. Well, we know that pi is approximately 3.14, so in decimals, half of pi is roughly 1.57. A right angle is just 1.57 radians, or pi over 2 radians. So the number for a right angle in this radian measure is 1.57. Well, you might be more familiar with 90 degrees. You know, you measured that on this protractor when you were at school. Well, in fact, that comes from the Babylonian measure. They took a circle and they divided that into 360 degrees, so a quarter of the way around would be 90. So 90 degrees, of course, is another expression for a right angle. And in fact, degrees, that's another way for measuring angles.
Right. Now let's see, that's 25 meters 50. All right, so that's the distance from the bottom of the tree to the bench, 25, 50. Now, of course, it's all very well, the story of Alan with his horse and his angles and his arcs and all the rest of it. But what I really want to know is something quite simple. Is the height of that tree there more or less than this distance I just measured? Now, I wonder what Alan can tell us about that.
Well, trigonometry is the branch of mathematics that connects angles with heights and distances. Look at this new angle. It's 0.68 radians. The ratio between the curved arc and the radius is 0.68. But to deal with the case where the side that's opposite the angle is not an arc, but an upright straight line, we must look at ratios in a right-angled triangle. The side opposite the angle measures 8 in some units of length, and the base of this triangle is now 10 units. So the ratio of the opposite side over the base is 8 over 10, 0.80. Well, the upright could always have been drawn in another place to make a different size triangle. If the opposite side now measures 4, the base is 5, the ratio is now 4 over 5, which is again 0.80. It turns out that whatever size triangle we take, the ratio of these two sides always stays the same. However, this ratio of 0.8 is different from the arc over radius ratio, which was 0.68 radians, so we must give it another name. Well, if you take a protractor, you can actually measure this angle. You'll find it's 38.7 degrees. And we call the 0.8 ratio the tan of the angle. That's just short for tangent. So we can write the tan of 38.7 degrees is 0.80. And tangents have been tabulated for every angle. For example, tan of 26.6 degrees is 0.5. The tangent of 45 degrees is precisely 1 because the height and the base are exactly the same length. And the tangent of 63.4 degrees turns out to be 2. In fact, the tangent of any angle can easily be found. All you've got to do is push the right button on your calculator.
Well, now we begin to see daylight, you see, because with this tangent idea that you've just seen explained so nicely by Alan, I think I can solve the problem of the tree. You see, just think about it. I already know the distance along the ground between the bench here and the bottom of the tree. So if I can find some way of measuring the angle between the ground and the line from the bottom of the bench to the top of the tree, that angle there, then I can use the idea of the tangent of the angle to calculate the height of the tree. So the problem is, how do I measure the angle? Well, I'm going to do it with this, which I don't habitually carry around in my pocket, but somebody kindly provided me with it. Christopher Columbus would probably recognize a thing like that, except for the plastic. So what I have to do is to put that down by the edge of the bench and then just sight up this kind of gun sight thing here up to the top of the tree. Well, you've probably realized that the angle that really interests me is 45 degrees, because you remember Alan explained that the tangent of 45 degrees is 1. So with 45 degrees, you'd have a height and a base which are exactly equal, and that would be the point at which I would be thinking about moving a little bit further back. So let's see. Oh, no, that can't be right. No, I've gone a bit too high. Well, that's just as well, isn't it? So say about there. What have we got here? 43 degrees. All right, I'll just see if I can work that out now. Well, now suppose I call the height of the tree here h. And then the angle I just measured is this angle here, and that was 43 degrees. So I know that the tangent, tan 43 degrees, is equal to the height of the tree divided by that length I measured, 25.50 meters. So the height of the tree is equal to 25.5 times tangent of 43 degrees. So let's just work that out. 43 tan times 25.5 equals, well, that's 23.7. 23.7 meters. So I've got about 2 meters in hand. Right, so let's go and mark that off, shall we? 2 meters. Well, 1, 2. Say about there. So that's where I figure the top of the tree will come to, and I've got a little margin of safety, so maybe I can just go and sit and watch them cut it down.